Now that we've got the basic operations of matrices down, including matrix multiplication, we're going to look at factoring matrices. In particular, we're going to look at a technique called LU factorization, or lower upper factorization. Now, the idea in here is to rewrite a matrix A as a lower triangular matrix times an upper triangular matrix. And remember, a lower triangular matrix is a matrix that has entries along the diagonal, entries below the diagonal, but it must have 0 entries above. This is going to be our lower. And an upper triangular matrix is the other way around. It can have non-zero entries on the diagonal. They can be 0, but they could be non-zero. You have potentially non-zero entries above the diagonal, upper, and you have all zeros below the diagonal. So the idea is to rewrite this matrix A as a lower triangular times an upper triangular. So to do this, we're going to introduce the idea of an elementary matrix. An elementary matrix is a matrix that is one elementary row operation removed from the identity. And the idea is you can mimic elementary row operations with multiplication by elementary matrices. So first out, there are 3 elementary row operations, so there should be 3 types of elementary matrices. So the first thing you could do is switch 2 rows. That was the first elementary row operation. So if we take the identity matrix, let's do this in the 3x3 case. 0, 1, 0, 0, 0, 1. So what we should do here, let's just say we were switching the first 2 rows. So that would give us 0, 1, 0, right? We're going to move the second row to the top and the first row to the middle. 0, 0, 1. So this is our first elementary matrix, and its inverse, the inverse of switching 2 rows, is to switch them back. So we're going to take the identity matrix and switch the same 2 rows. So that just actually gives us the same elementary matrix. That should be 0, 0, 0, 1. So this is the elementary matrix. This is its inverse. And you can verify that if you matrix multiply these together, you get the identity. They cancel. Okay. Also, after switching 2 rows, we can multiply a row by a non-zero scalar. So if we were to take the identity matrix, 0, 1, 0, 0, 0, 1, and multiply a row by a scalar. Let's say we multiply the top row by C. That'll give us the matrix C, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and then its inverse, the inverse of that, to undo that operation, we'd have to divide the top row by C. That's why we insisted that this the scalar multiple not be 0. It has to have a reciprocal. So we'll take the identity matrix and multiply the top row by 1 over C. And the bottom 2 rows will be unchanged. So this is the inverse of this elementary matrix. And finally, the last thing we can do is we can add a multiple of one row to another. So let's say we take the identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, and let's add C times the first row to the second row. So that gives us the first row stays unchanged. We're adding C times the first row to the second row, which makes this C 1, 0, 0, 0, 1. Now the inverse of adding C times the first row to the second row is adding negative C times the first row to the second row. So if we add negative C of the first row of the identity to the second row, we get negative C 1, 0, 0, 0, 1. And again, for all of these, you can go through and quickly verify by matrix multiplication that these two are in fact inverses. Those two are inverses. Those two are inverses. So how does this help for factorization? Well, the idea here is you're going to take a matrix A, and you're going to row reduce this to an upper triangular matrix. You're going to do Gaussian elimination, so you wind up with an upper triangular matrix. Now, when you do this elementary row operations to reduce this, what you're really doing is you're taking the matrix A, you're multiplying it by one elementary matrix after another. So you're multiplying A, but you're repeatedly row reducing it, that is multiplying by elementary matrices, and getting the answer of U with an upper triangular on the end. Now if you multiply both sides by the inverse of this set of elementary matrices, you get E1 inverse, E2 inverse, and so on up to En inverse times U. And the goal is to ensure that this is a lower triangular matrix. Then we've reduced A to a lower times an upper. Let's do an example of this. Let's say we have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and our goal is to LU factor this. So to do that, again, we're doing what we've been doing all along in reducing these matrices. We're going to put it into row echelon form. So to do that, I want to get rid of everything in this first column. I already have a leading one here. So I can do that by multiplying the first row by -4 and adding it to the second row. So that's the same. If I want to get my figure out my first elementary matrix, let's take the identity 1, 0, 0, 0, 1, 0, 0, 0, 1, and we'll do the same elementary row operation to the identity as we're doing to our matrix. So we're going to take -4 times the first row and add it to the second. So this gives us 1, 0, 0, -4, 1, 0, 0, 0, 1. This here is our first elementary matrix. So that says that E1 times A is, well, first row stays. The second row, we take -4 times the first, add it to the second. So -4 plus 4 is 0. -8 plus 5 is -3. And -12 plus 6 is -6. And then the bottom row stays as is, 7, 8, 9. Okay, now to get our next elementary matrix, I know that I want to get rid of the 7 here, so I'm going to take -7 times the first row and add it to the third row. So let's start with our identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, and perform that same elementary row operation. Multiply the first row times 7 and add it to the bottom row. So this gives us, well, our first two rows stay unchanged, and our last row picks up a -7. So this is the matrix E2. Okay, so now from here, so that says that E2 times E1 times A, right? We've done one elementary row operation to get it to this point. We've done our second one now. So this leaves the top row is 1, 2, 3, 0, -3, -6. Now the bottom row, -7 plus 7 is 0. -14 plus 8 is -6. -21 plus 9 is -12. So we're almost there. Now our goal is to make this upper triangular. So the only thing we need to get rid of is the 6. So to do that, we can multiply the second row by -2 and add it to the bottom. So that means for our elementary matrix, well, we're taking the identity 1, 0, 0, 0, 1, 0, 0, 0, 1, and we're applying that same elementary row operation. Multiplying the middle row by -2 and adding it to the bottom. So this gives us 1, 0, 0, 0, 0, 1, 0, 0, -2, 1. That's our E3. Okay, now if we do that on our matrix, we've got E3 times E2 times E1 times A is, well, the top row stays, we're not changing that. The middle row stays. And the bottom row, 6 plus -6 is 0. 12 plus -12 is 0. Okay, so now we've got an upper triangular matrix. Now, the fact that we have a 0 on the diagonal, that's okay. This is still upper triangular. The fact is that the only non-zero entries are in this upper triangle right here. We can have zeros over in the upper triangle, but we can't have zeros anywhere else. So this is an upper triangular matrix. So here, this is our U. Now let's go through and find our LU factorization. So A now, if we get rid of each one of these in turn, this will be E1 inverse, E2 inverse, E3 inverse, times U. So let's actually multiply out this these E's. So E1, was this matrix right here. The only non-identity feature in this is a -4 in the second row, first column. So its inverse will have a +4 there. So this will be 1 0 0 4 1 0 0 0 1. That's E1 inverse. Now E2 inverse. I see the only non-identity feature on here is the lower left-hand corner is -2. So our inverse, it'll be a +2. 1 0 0 0 1 0 2 0 1. And E3, this matrix right here, now its inverse, remember we're going to have to add, instead of adding -2 of the middle row to the bottom row, we'll add +2, so it'll make that a +2. So that means this is 1 0 0 0 1 0 0 2 1 times u. So let's actually multiply these together. Now I see that this is a lower triangular matrix, this is a lower triangular matrix, and this is a lower triangular matrix. When you multiply two lower triangular matrices, you're guaranteed to get another lower triangular matrix. And the same goes with upper. So I know that this is going to work out. This will give us a lower. Let's actually go through and do this. If we multiply the first two, we take the first row here times the first column here, we get 1. First row times second column, we get 0. First row times third column, we get 0. Okay, now for the second row. We take the second row times the first column, we get 4. Second row times second column, we get a 1. Second row times third column, we get a 0. Now for the bottom row. We take the bottom row times the first column, we get a 2. We take the bottom row times the second column, we get a 0. Take the bottom row times the third column, we get a 1. And now we've got to multiply this by the next matrix. 1 0 0 0 1 0 0 2 1 times u. This is still our A. Okay, we'll do the same thing. So this is, in order to get the first row, first column entry, we take the first row times the first column, gives us 1. The first row dotted with the second column gives us 0. The first row dotted with the third column also gives us 0. Okay, now for the second row, we take the second row times the first column, second row times the first column, we get 4. Second row times second column, we get 1. Second row times the third column, we get 0. Okay, now for the bottom row. We take the bottom row times the first column, we get 2. We take the third row times the second column, we get 2. And then the bottom row times the right-hand column, we got 1. So this is our lower triangular times our upper triangular u we identified before to be 1 2 3 0 -3 -6 0 0 0. So now we factored our matrix A into a lower triangular times an upper triangular, and that's matrix factorization.